A new era of space exploration is upon us. We stand at the cusp of a new era in space exploration. Our reach has been limited. We've sent probes and rovers, even humans, to our celestial neighbours, but our journeys have been slow and inefficient. The vast distances of space demand a new kind of spacecraft. They demand the power of nuclear propulsion.
The idea of nuclear spaceships is not new. In the 1960s, the United States developed the Phoebus 2A reactor. This marvel of engineering was a technological leap forward. It was a high-powered nuclear thermal rocket engine. The Phoebus 2A promised faster travel times and larger payloads. It offered a glimpse into a future where humanity could venture deeper into the cosmos. But the promise of Phoebus 2A was never fully realized. President Nixon's vision for space exploration focused on the Space Shuttle program. This program, while groundbreaking in its own right, prioritized reusable spacecraft over deep space exploration. As a result, funding for nuclear rocket development dwindled. The dream of harnessing the atom for space travel was put on hold.
The military, however, recognized the strategic value of nuclear propulsion. They saw the potential for rapid deployment of assets in space. Nuclear rockets could power surveillance satellites, missile defense systems, and even space-based weapons platforms. The Pentagon's interest kept the technology alive. It funded research and development, albeit at a reduced scale.
Nuclear thermal rockets, or NTRs, are a class of rocket engines that use a nuclear reactor to heat a propellant. The propellant, typically hydrogen, is pumped through the reactor core. It is heated to extremely high temperatures and expelled through a nozzle, generating thrust. NTRs are far more efficient than their chemical counterparts. They can produce twice the thrust for the same amount of propellant. This translates to shorter travel times and increased payload capacity. Overcoming early obstacles. Early NTR designs faced significant challenges. One of the main hurdles was hydrogen corrosion. The intense heat generated by the reactor caused the hydrogen propellant to eat away at the engine components. Another problem was reactor shedding. Tiny particles of nuclear fuel would break off from the reactor core and be expelled with the exhaust. This posed a significant radiation hazard.
DRACO, a new hope. Today, a new generation of scientists and engineers is reviving the dream of nuclear spaceships.
The Defense Advanced Research Projects Agency, or DARPA, and NASA have partnered on the demonstration rocket for agile cislunar operations known as DRACO.
DRACO aims to develop and test a safe, reliable, and high-performance NTR engine. It represents a major step forward in nuclear space propulsion. Safety and innovation in design. The DRACO project incorporates several innovative design features to address the challenges of the past. The reactor core is made from advanced materials that are resistant to hydrogen corrosion. The engine also utilizes a novel fuel containment system. This system prevents reactor shedding and minimizes the risk of radioactive contamination.
Safety is paramount in the DRACO project. The engine is designed to be launched on a conventional rocket and only activated once it reaches a safe orbit.
The future of space travel. The successful development of DRACO could revolutionize space travel. Nuclear-powered spacecraft could significantly reduce travel times to Mars and beyond. This would open up a new era of human exploration and scientific discovery. We could establish permanent outposts on the Moon and Mars. We could mine asteroids for valuable resources. We could even send robotic missions to the outer solar system and beyond. The possibilities are as vast as the cosmos itself.
Indeed, the future of space travel holds boundless potential.